Hey everybody, this is Mr. Schaefer. So we're getting ready for that 2020 AP Calculus exam, and I have for you today a mock exam presentation that should take us approximately 25 minutes. It is an FRQ, sort of a super FRQ, so it's much longer than the traditional ones that College Board has published in the past. This one, I need to thank Brian Passwater for authoring this FRQ. It's an excellent question and it really gets at a variety of calculus topics, all within one sort of, again, 25-minute FRQ. So it's a great series of questions all contained in one exam. I wanted to walk you through the solution guide to this FRQ. We will not need a calculator. You can certainly have one, but it is not a requirement to use one on this problem. So to begin, we have this picture of f prime, and that's maybe the first thing to notice is that we're looking at the graph of the derivative of f. That's always important to know what you are looking at. And then g is defined down here as a piecewise function. And then there's all this given information as well, which you can read. We're going to jump right into letter A, the opening part of this problem, which says to show that function g is continuous at the point x equals 3. So there are three criteria that we need to make sure we establish to prove continuity of a function at a certain point. And the first one is this. Let's see if g of 3 exists. Well, if I use my piecewise definition, g of 3 would be that upper part. So g of 3 is going to be f of x squared minus 5, or 3 squared minus 5, since we're at 3. And that will simply become f of 4. So what is the value of f of 4? Again, I've got the picture of the derivative of f. So to go from a derivative back to the original function, we want to use integration. So let's build a definite integral. And there's this other piece of info here listed in the given statements. F of 6 equals negative 4. Why don't we use a strategic bound of 6 along with our bound of 4? So a lower bound of 4 and an upper bound of 6 across the derivative function. So here's what we're going to integrate. The integral from 4 to 6 of f prime by ftc would be the antiderivative evaluated at the upper bound minus the lower bound. That's the fundamental theorem of calculus. And again, keep in mind that we're searching for the value of f of 4. Now, the integral from 4 to 6 of f prime can be found by simply looking at the area under the function f prime from 4 to 6. And so here's that region. It says the area is 3, but because the region is below the x-axis, it's really going to be negative 3. F of 6 is given to be negative 4, and then I'm hunting for this value f of 4. Well, rearrange some terms here and use some algebra. We can find that f of 4 has to be equal to negative 1. So all that to say f of 4 is negative 1, which really means g of 3 is negative 1. Now, second piece of criteria for continuity. We've got to use the left and the right-sided limits as x approaches 3. So you must write down on your FRQ the limit as x approaches 3 from the left of our function and the limit as x approaches 3 from the right of our function. So from the left side of 3, we're going to be dealing with f of x squared minus 5. And direct substitution will work just fine. From the right side of 3, we'll have 5 minus 2x. And because those two limits match, the left and the right sided limits match, then I can make this claim, and this should be written down on your FRQ as part of your proof. The limit as x approaches 3 overall of function g is therefore equal to negative 1. And the third criteria for continuity is just to state that the limit and the function value both are the same. So g of 3 and the limit as x approaches 3 of function g both are equal to that value, in this case of negative 1, and therefore I can claim that g is continuous at x equals 3. Part B. Find the absolute maximum value of f on the interval from -2 to 10. I'm going to be thinking about using the candidates test whenever I see absolute maximum or minimum across a closed interval, so the closed interval test or the candidates test. And it's really the extreme value theorem that lets us find these cases here. So I'm going to make a table here. X and f of x. -2 and 10 are both endpoints that have to be included. And now I'm searching for maximum values of f. Well, basically think about when f prime is equal to 0, and more specifically changes from positive to negative. Because if you can find points where that happens, then you have a local maximum or a potential absolute maximum as well. So we're going to find places on f prime where we have a 0 and the derivative changes from positive to negative. And if you look at the picture here, the only place I see that happening would be right there at x equals 4. So x equals 0 and x equals 6, x equals 9, those are also critical points. However, it's only at the point 4 where I have a change of f prime that goes from positive to negative. So let's put 4 in there as a critical point candidate. And now I'm interested in basically finding f of -2, f of 4, and f of 10. One of those three has to be the absolute maximum, so let's find out who wins. Now to find these values, I'm going to go back to that f of 6 definition. Since I know that f of 6 was given as, was it -4? Yes, f of 6 is -4. I'm going to use that to again write some strategic integrals. So f of -2 by ftc, that's going to be f of 6 minus integrating from -2 up to 6 of f prime. F of 4 will again be f of 6 minus the integral from 4 to 6 of f prime. To find f of 10, we start at f of 6 this time, so I'm adding the integral from 6 to 10 of f prime. So I'm generating all these statements by using FTC and sort of manipulating the terms as well. And when we're finished, we're going to find out that the winner ends up being down here. F of 10 has a value of 7. I believe this value is -7. F of 4 ends up being -1. And so the winner overall is +7. And make sure we answer the question. It says find the absolute maximum value, which would mean the actual output here. 7 is my answer, not 10. It occurs at 10, but the value itself would be 7. So we might say f has an absolute maximum value of 7. And we essentially are using the extreme value theorem and the closed interval test or the candidates test to complete that justification. Part C. Here's a new function, function k. And it says function k, or it is known that the limit as x approaches 3 can be evaluated using L'Hopital's rule. So what that means is, let's see if we can analyze what's happening here with the numerator and the denominator for L'Hopital's rule. What is the limit as x approaches 3 of the numerator? So 3 times the integral from 4 to 3x of f prime t dt minus 4x. If I plug in a 3, and I try this with direct substitution, we'll get 3 times the integral of 4 to 9 of f prime minus 12. And from 4 to 9, that area is going to be a -3 plus a 7, so a net result of 4. So I have 3 times 4 minus 12, or 0, when we're all finished. If that's the case, then the limit of the denominator must also be 0 if L'Hopital's rule is going to be effective. So I'm going to end up with this indeterminate form of a 0 over 0. So this limit, as x approaches 3, of the denominator, 3e to the power of 2f of x plus 5 minus x must be equal to, by direct substitution, f of 3 plus 5, and then minus 3. But again, because L'Hopital's rule works here, that has to all equal 0 at some point. So I'm going to add 3 across. And what if we divide by 1? I'll do a couple steps of algebra sort of all in one here. So I'm going to get e to the power of 2 f of 3 plus 5 equal to 1. Switch that into log form. So natural log of 1 is going to be 0. So 2 f of 3 plus 5 equals 0. And f of 3 will have to equal negative 5 over 2. There's f of 3, which is the first part of my problem. And then it says to find the limit as x approaches 3 of k. So then I'm going to actually use L'Hopital's rule to find that limit value. I'll slide over here to do that. Here we go. Limit as x approaches 3 of k of x can be equal to the derivative of the numerator, which is going to be a 3, and then here's second FTC. I'm going to dump in that 3x into t. Don't forget to multiply by 3, the chain rule, the derivative of the upper bound, and then a minus 4, all divided by chain rule down here. So I have 3e to the 2f of x plus 5 times natural log of e times the derivative of the exponent, which is going to be 2f prime. All of that is the derivative of my exponential function, and then there's a minus 1 out there too. So let's not lose track of that negative 1. Direct substitution, plug in 3 and see what we can clean up here. 3 times f prime of, that'll become a 9, actually 9 times f prime 9 minus 4 all over 3e to the 2 times, let's see, that'll all be a 0 here. So e to the 0 is 1. So I'll have a 3 times 2 f prime of 3 minus 1. 9 times 0 minus 4, f prime of 9 is 0, divided by 6, f prime of 3 minus 1. Check the slope of f, or check the value of f prime, I should say, at 3. I believe it's 3.5. So when we're all finished, I'll have a negative 4 in the numerator, divided by 20 for a limit of negative 1/5. That's a pretty challenging problem, very challenging problem, involving L'Hopital's rule. So there's f of 3, negative 5/2, and then the limit as x approaches 3 of k of x, negative 1/5. Moving right along, part D. Here's another function, a new function h. And h is defined, or it said y equals h, and its derivative dy dx is given. Y is always greater than 1/3. Find the second derivative. Well, I'm going to have to use product rule on this to find the second derivative. So let's do that. Derivative of the first times the second plus the first times derivative of the second. And then 3 times dy dx, essentially because it's implicit differentiation. But then dy dx is that entire expression, so let me just replace it with all this once again, f prime 2x times 3y minus 1. And then use the expression to determine if the graph of h is concave up or concave down. So let's evaluate d squared y dx squared, the second derivative at the ordered pair 1, 2. So f double prime of 2 times 5 plus f prime of 2 times 3. times f prime of 2 times a5 once again. Now, I don't really know what the value is. I don't really care what the value is. I just care that the sign of the second derivative in this case is going to be positive. So since that is all going to be positive, you can double check that work. Then I can make the claim that h of x is concave up. Reason? Because my second derivative at the ordered pair 1, 2 is positive. So I have a concave up value for that problem. Letter E. Sticking with function h, find the interval or intervals where function h is increasing. So h is going to be increasing whenever its derivative is positive. And its derivative, again, is dy dx. So I'm hunting for the intervals where that is going to be true. Now, the derivative is f prime of 2x times 3y minus 1. And if I set that equal to 0 and just do a quick little analysis on that, either f prime of 2x will be 0, or 3y minus 1 will be 0, but we established earlier on that for this entire function, h is defined over values where y is greater than 1/3. And this is going to become equal to 1/3, so that expression will always end up being positive. So basically, I'm searching for places where f prime of 2x is going to be positive. On what intervals does that happen? Let me change that to an inequality because that will be where f is increasing. Well, where is f prime positive? If I go way back here to the picture and I look at f prime, which is this graph, I see that from the intervals 0 to 4, and then again from 6 to 10. So 0 to 4 and 6 to 10. F prime of 2x is positive, or f prime is positive. Let's see. F prime of x, I should say, is positive on 0 to 4 and 6 to 10. But those aren't our answers because the expression here from the derivative is f prime of 2x. So to adjust for that 2 inside, we want to divide these intervals by 2 individually to convert them into these 0 to 2 and then 3 to 5. Okay, so think about dividing by 2. So those are my intervals when h is increasing. And the reason? Because its derivative is positive. All right, and then lastly, letter F. Consider the differential equation from part D. Use separation of variables to find a general solution. And notice it says here in this form, so I don't have to go all the way to isolating y. Normally for separation of variables problems, we start by separating. We say we separate the variables first, and then we integrate. Left and the right, we'll get a constant of integration. And then finally, we will isolate or evaluate y, but we don't need to here. It says we can stop at that form, natural log of 3y minus 1. So the differential equation from part D, there it is once again, dy dx. What if we divide by 3y minus 1 and then multiply by dx? In doing so, we'll be able to separate the variables and form an equation that looks like this. 1 over 3y minus 1 dy equals f prime of 2x times dx. There's the separation step. Now let's do the integration step. Separate, integrate. On the left-hand side, natural log of 3y minus 1. Watch out for the chain rule. Divide by the derivative of that denominator, and we'll get division by 3, or 1/3 on the outside here. Plus c, I'm going to tack on the other side. The antiderivative of f prime is simply f. But again, another reverse chain rule here. Divide by the derivative of the inside here, which is going to be a 1/2, or division by 2, or 1/2. And then don't forget plus c, the constant of integration. Finally, let's get the natural log isolated. So multiply everything by 3. And I'm going to end up with this expression, or this equation, I should say. Constant times 3 remains a constant. And there's the form that the problem wanted. So if I check this here carefully, I'll have an a multiplier there, which is 3/2, and then a b multiplier on the inside of f, which is just regular 2. The entire equation is set in that form. There's the general solution in the form that the problem wanted. So that's how this problem works. I hope you're able to stick with me for the whole time, and I hope that was helpful and informative for you. Good luck to you in the rest of your studies.